So this podcast involves nuclear decay and radiation. We have taken a look at the three types of radiation: the alpha particle, the beta particle, and then high energy gamma radiation. This chart that you see on the slide here kind of summarizes all three of those. So it shows you here with alpha radiation the symbol. It is a helium nucleus, so it has a mass number of 4, atomic number of 2. And then beta radiation is simply an electron there, so it has a mass of 0 and an atomic number of -1. And then of course gamma radiation is high energy. Some of the more common sources there: radium-226 is a common alpha radiation source, carbon-14 beta radiation, and then cobalt-60 gamma radiation. The penetrating power is quite interesting down there towards the bottom. The alpha radiation is not very penetrating, so you can shield yourself from alpha radiation with clothing and a simple sheet of paper. Beta radiation is a little bit more penetrating, so metal foil actually serves as a pretty good protecting covering. And then gamma radiation, which is quite similar to X-rays there. If you notice that lead and concrete act as shields to gamma radiation, and if you go in and you have an X-ray done, at the dentist's office, they put that lead apron on you to protect the rest of your body from the X-rays. So this is a great table, one that you may want to screenshot and print out, because it does compare all three types of radiation pretty effectively. Now this next slide, elements will decay if they are radioactive until they become stable. And the solid line that you see in here is actually called the line of stability. And all elements in the periodic table will decay to kind of follow that line. So notice the y-axis is the number of neutrons and the x-axis is the number of protons. So there's a certain little ratio of those two that is more stable, and the ratio is basically a 1-to-1 ratio between the two. So elements will typically decay to try to get close to this 1 neutron for every 1 proton line of stability. The most stable nuclide is iron-56. When the atomic number gets greater than 83, you typically get some radioactivity. So usually below that, you don't get a ton of elements that are radioactive, and you can actually look at the periodic table and see that. Now, this is a particular element. This is uranium-238, and it actually will go through an entire pathway of decay to reach a stable state. So in the upper left corner there you see uranium-238, and then across the top you see an alpha particle given off, then a beta and a gamma, and then a beta and a gamma, all the way down to the bottom left where it's labeled stable isotope. Once that uranium-238 reaches lead-206, it's reached a stable isotope, so it will stop decaying. As it decays, there is also a half-life associated with the decay, and that's what we want to take a look at next. So this is the stepwise decay of uranium-238 all the way down to its most stable end isotope, which is lead-206. Now I mentioned half-life in the last slide. Half-life is, well, it's basically what it sounds like it is. Every certain time period, half of the original radioactive isotope will decay to its most stable isotope, or most stable product. And this actually shows kind of the exponential change here of a particular isotope over time. So again, half-life is the amount of time it takes for half of a given sample of a radioactive isotope to decay to a stable substance, a stable element. Now, we can actually calculate half-lives, and in this particular course we're not going to do that, but this equation allows us to take a rate constant for a particular element and determine the half-life. So that t to the 1/2 stands for half-life, and then the k is actually a rate constant associated with that particular element. And again, we're not going to calculate half-lives in here. But we should take a look at some sample half-lives. So one of the most common radioactive isotopes is carbon-14, and as you can see here, the half-life is approximately 5,700 years, and the main radiation emitted there is beta radiation. Notice how the half-lives vary here from, a couple days through thousands of years. There are elements too that have half-lives that are just seconds, so it's very hard to isolate those elements because they decay so quickly over a very short period of time. So in the next next series of slides, we'll take a look at nuclear fusion and nuclear fission.